Welcome back. Before we start our deep dive into today's topic, please take a second to hit that like button, subscribe to the channel, and turn on notifications so you never miss a technical breakdown. It really helps the channel grow. Welcome to today's deep dive into Apache Uniffle, a game-changing technology that's redefining how we handle shuffle operations in big data processing. Traditional frameworks like Spark and MapReduce suffer from inefficient local disk-based shuffles that create bottlenecks and performance issues. Apache Uniffle solves this by introducing a remote shuffle service architecture that dramatically improves data processing speeds. This isn't just an incremental improvement, we're talking about transformative changes that can reduce job completion times by up to 80% in many scenarios. Whether you're running on-premises clusters or modern cloud environments, Uniffle provides the foundation for next-generation analytics workloads. So what exactly is Apache Uniffle? At its core, it's a remote shuffle service designed to optimize the critical shuffle phase in distributed computing workloads. As an open-source project under the Apache Software Foundation, Uniffle provides a vendor-neutral solution that works seamlessly with popular frameworks like Apache Spark, MapReduce, and Tez. The shuffle phase is where intermediate data is redistributed across the cluster, and it's traditionally been one of the biggest performance bottlenecks. Uniffle addresses these fundamental limitations by moving shuffle data off local disks and into a centralized, optimized service layer. This architectural shift enables better resource utilization, improved fault tolerance, and dramatically faster job completion times. To truly appreciate Uniffle's value, we need to understand the shuffle performance problems it solves. In traditional distributed computing, each node writes shuffle data to its local disk, creating massive I/O bottlenecks that can bring even powerful clusters to their knees. Network inefficiencies compound these issues, as data must be transferred multiple times between nodes in inefficient patterns. Fault tolerance becomes problematic because losing a node means losing all its locally stored shuffle data, requiring expensive recomputation. Additionally, resource contention between compute tasks and shuffle I/O operations degrades overall cluster performance. These interconnected challenges have plagued big data workloads for years, limiting scalability and performance in production environments. Apache Uniffle's architecture represents a fundamental shift from traditional shuffle mechanisms. Instead of relying on local disk storage, Uniffle introduces centralized shuffle servers that manage the entire data lifecycle. Client applications write shuffle data directly to these remote services and read from them during reduce phases, eliminating the need for intermediate local storage. This decoupled architecture allows compute resources and shuffle storage to scale independently based on workload demands. Built-in fault tolerance mechanisms ensure data durability through replication and automatic failover capabilities. The result is a robust, scalable solution that addresses all the performance and reliability issues we discussed earlier. Let's examine the key components that make Apache Uniffle work. First, we have the shuffle servers, which are the workhorses of the system. They store shuffle data, manage its lifecycle, and serve it to clients when requested. The coordinator acts as the brain of the operation, maintaining cluster state, handling server registration, and routing client requests to appropriate servers. Client libraries provide the application interfaces that frameworks like Spark use to interact with the shuffle service. Finally, the storage backend is pluggable, allowing administrators to choose from various storage implementations including memory, local disks, or even cloud storage solutions. This modular design provides flexibility while maintaining high performance across diverse deployment scenarios. Understanding the workflow is crucial to appreciating Uniffle's elegance. When a job starts, clients first register with the coordinator, which assigns them to appropriate shuffle servers based on load balancing and data locality considerations. During the map phase, tasks write their shuffle data directly to these assigned remote servers instead of local disks. This eliminates local I/O bottlenecks and enables more efficient data management. In the reduce phase, tasks fetch their required data directly from the remote servers, bypassing the traditional shuffle file transfer mechanisms. Finally, the system automatically handles cleanup operations, removing stale data and freeing resources without manual intervention. This streamlined workflow dramatically reduces job completion times while improving resource utilization. The performance advantages of Apache Uniffle are nothing short of remarkable. Real-world deployments have shown job completion time reductions of up to 80% compared to traditional shuffle mechanisms. This dramatic improvement comes from several factors. First, consolidating shuffle I/O operations on dedicated servers with optimized storage configurations dramatically improves disk efficiency. Second, the intelligent routing of data between servers reduces network chatter and optimizes bandwidth utilization. Third, by offloading shuffle operations from compute nodes, we significantly reduce garbage collection pressure and memory fragmentation. These improvements compound to create a system that can handle much larger workloads with better resource utilization, making it ideal for demanding analytics and machine learning applications. Reliability is paramount in production big data environments, and Apache Uniffle delivers robust fault tolerance mechanisms. Data is automatically replicated across multiple shuffle servers, ensuring that the loss of any single server doesn't impact job completion. When servers become unavailable, the system automatically fails over to healthy replicas without requiring job restarts. For mission-critical workloads, administrators can configure persistent storage backends that survive server restarts. Even during partial system failures, Uniffle gracefully degrades performance rather than failing completely, maintaining job progress and minimizing disruption. These reliability features make Uniffle suitable for production environments where uptime and data integrity are non-negotiable requirements. One of Uniffle's most significant advantages is its sophisticated resource management and isolation capabilities. By dedicating separate resources to shuffle operations, we eliminate the resource contention that plagues traditional architectures where compute and I/O compete for the same system resources. The system dynamically allocates resources based on real-time workload demands, ensuring optimal performance during peak usage while conserving resources during lulls. Fine-grained memory and CPU quotas prevent any single job from monopolizing shuffle server resources, ensuring fair sharing across all workloads. Comprehensive monitoring and alerting capabilities provide administrators with the insights needed for effective capacity planning and performance optimization. Apache Uniffle's pluggable storage architecture provides unprecedented flexibility in how shuffle data is stored and managed. The system employs a memory-first approach, keeping hot data in fast memory storage while automatically spilling to disk when capacity is exceeded. This hybrid approach maximizes performance while ensuring data durability. For cloud-native deployments, Uniffle can integrate directly with cloud storage services, enabling hybrid and multi-cloud architectures. Organizations with specialized requirements can even implement custom storage backends tailored to their specific needs. This flexibility ensures that Uniffle can adapt to diverse deployment scenarios while maintaining optimal performance characteristics. Integration with Apache Spark, one of the most popular big data processing frameworks, is remarkably straightforward. Uniffle provides a plugin that seamlessly replaces Spark's default shuffle manager without requiring any changes to application code. This means you can start benefiting from Uniffle's performance improvements immediately, without costly rewrites or complex migration processes. The integration works across all Spark execution modes, including local, standalone, Yarn, Mesos, and Kubernetes deployments. Best of all, existing Spark monitoring and management tools continue to work unchanged, providing a smooth transition path for organizations looking to modernize their shuffle infrastructure. Apache Uniffle supports multiple deployment architectures to fit different organizational needs and existing infrastructure. For dedicated clusters, standalone deployment provides maximum control and performance optimization. In resource-managed environments, Yarn integration allows Uniffle to leverage existing cluster resource allocation mechanisms. Kubernetes support enables containerized deployments that align with modern cloud-native practices, including automated scaling and management. For cloud deployments, Uniffle's architecture supports auto-scaling capabilities that can dynamically adjust resources based on workload demands. This deployment flexibility ensures that organizations can adopt Uniffle regardless of their existing infrastructure choices while maintaining optimal performance and operational efficiency. Effective monitoring and observability are critical for maintaining optimal Uniffle performance in production environments. The system provides comprehensive metrics covering everything from shuffle server health and resource utilization to detailed performance indicators like data transfer rates and latency measurements. Integration with popular monitoring systems like Prometheus, Grafana, and enterprise solutions ensures that administrators can leverage their existing tooling investments. Real-time dashboards provide operational visibility into cluster health and performance trends, enabling proactive management. Advanced alerting mechanisms can automatically notify administrators of potential issues before they impact workload performance, ensuring smooth operations and minimal downtime. Security is a fundamental consideration in any enterprise deployment, and Apache Uniffle provides robust security features to protect sensitive data and operations. The system supports standard authentication and authorization mechanisms, ensuring that only authorized clients can access Shuffle services. Data encryption protects Shuffle data both in transit and at rest, meeting regulatory and compliance requirements for sensitive workloads. Network isolation capabilities enable secure multi-tenant deployments where different teams or organizations can share infrastructure without data exposure risks. Comprehensive audit logging provides detailed records of all Shuffle operations, supporting compliance requirements and security investigations while maintaining operational transparency. Let's examine a compelling real-world use case. Financial services analytics where Apache Uniffle delivers transformative value. Financial institutions process massive datasets for risk analysis, requiring sub-second processing times to make critical business decisions. Traditional Shuffle mechanisms simply can't keep up with these demanding performance requirements. Uniffle's architecture enables these organizations to process complex ETL pipelines with large Shuffle operations efficiently and reliably. The security and audit capabilities meet stringent regulatory compliance requirements, while multi-tenant isolation ensures that different business units can operate securely on shared infrastructure. This combination of performance, security, and operational efficiency makes Uniffle an ideal solution for the demanding requirements of financial analytics workloads. Let's look at concrete performance metrics that demonstrate Apache Uniffle's impact in real-world deployments. Organizations consistently report up to 80% reduction in job completion times, transforming hours-long processes into minutes. Resource utilization improves by approximately 60% as compute nodes are freed from Shuffle I/O responsibilities, allowing them to focus entirely on processing tasks. Shuffle-related failures decrease by an impressive 90% thanks to Uniffle's robust fault tolerance mechanisms and centralized data management. Network efficiency also improves significantly, with up to 50% reduction in Shuffle-related network traffic through optimized data routing and consolidation. These metrics translate directly into cost savings, improved agility, and enhanced competitive advantage for organizations leveraging big data analytics. Successful Apache Uniffle deployment requires careful attention to configuration best practices. Proper sizing of Shuffle server clusters is fundamental. Too few servers create bottlenecks, while too many waste resources. Memory allocation must be optimized based on workload characteristics, balancing between keeping hot data in memory and managing spillover to disk storage. Network configuration plays a crucial role in achieving optimal throughput, requiring consideration of bandwidth, latency, and topology. Storage backend selection should align with specific requirements for performance, durability, and cost. These configuration decisions directly impact system performance and reliability, making them critical success factors for any Uniffle deployment. As workloads grow and evolve, effective scaling strategies become essential for maintaining Apache Uniffle performance. Horizontal scaling allows organizations to add shuffle server capacity incrementally as demand increases, providing cost-effective growth paths. Dynamic resource allocation capabilities enable the system to automatically adjust resource assignments based on real-time demand patterns, optimizing utilization during both peak and off-peak periods. Intelligent load balancing distributes workloads evenly across server clusters, preventing hotspots and ensuring consistent performance. Capacity planning tools help administrators anticipate future needs and provision resources accordingly, ensuring that the system can handle peak workloads without performance degradation. These scaling strategies make Uniffle suitable for organizations of all sizes, from startups to enterprise-scale deployments. Even with careful planning, troubleshooting remains an important skill for Apache Uniffle administrators. Performance bottlenecks can arise from various sources, including network limitations, storage constraints, or configuration issues, requiring systematic diagnostic approaches. Network connectivity problems between clients and servers can impact job reliability and require methodical investigation using built-in monitoring tools. Memory pressure and spillover events, while handled automatically by the system, may indicate the need for configuration adjustments or resource scaling. Server failures, though gracefully handled by Uniffle's fault tolerance mechanisms, should be investigated to prevent recurrence and maintain optimal cluster health. Mastering these troubleshooting techniques ensures smooth operations and maximizes the benefits of Uniffle deployment. Apache Uniffle integrates seamlessly with modern data stack architectures, making it a valuable component in contemporary analytics environments. Cloud-native compatibility ensures that Uniffle works effectively in containerized deployments on platforms like Kubernetes, supporting auto-scaling and modern DevOps practices. Integration with data lake technologies enables unified data processing pipelines that can handle both batch and streaming workloads efficiently. The system's API compatibility means it can work alongside existing toolchains and processing frameworks without requiring disruptive changes. This integration capability makes Uniffle a future-proof investment that can evolve with changing technology landscapes while continuing to deliver performance benefits across diverse workloads and architectures. Looking ahead, Apache Uniffle's development roadmap promises even more exciting capabilities. Enhanced cloud storage integration will provide seamless connectivity with major cloud providers' storage services, enabling hybrid and multi-cloud deployments with optimal performance. Advanced machine learning optimization features will specifically target the unique shuffle patterns common in distributed training workloads, further improving performance for AI applications. Multi-cloud deployment support will become even more sophisticated, enabling organizations to leverage best-of-breed services across different cloud providers while maintaining consistent performance and management experiences. Enhanced security and compliance features will address evolving regulatory requirements and enterprise security standards, ensuring that Uniffle remains suitable for the most demanding production environments. Apache Uniffle benefits from a vibrant open-source community that drives continuous innovation and improvement. Active development ensures regular releases with new features, performance enhancements, and bug fixes that keep the platform current with evolving requirements. Multiple commercial vendors provide enterprise support options, giving organizations confidence in production deployments while contributing to the project's ongoing development. A rich ecosystem of plugins and extensions extends Uniffle's capabilities, enabling integration with specialized tools and workflows. This community-driven approach ensures that Uniffle evolves to meet real-world needs while maintaining the stability and reliability required for enterprise deployments. The combination of community innovation and commercial support creates a robust foundation for long-term success. Migrating to Apache Uniffle requires careful planning and execution to maximize benefits while minimizing disruption. Gradual rollout approaches allow organizations to validate performance improvements and identify any integration issues before full deployment, reducing risk and ensuring smooth transitions. Comprehensive performance benchmarking and validation against existing shuffle mechanisms provide concrete evidence of improvements and help optimize configurations. Compatibility testing with existing workloads ensures that all current applications continue to function correctly with the new shuffle service. Training and knowledge transfer programs prepare operational teams to effectively manage and troubleshoot the new system, ensuring long-term success and maximizing return on investment from the migration effort. While implementing Apache Uniffle requires initial investment in new infrastructure and configuration, the cost-benefit analysis strongly favors adoption for most organizations. Reduced hardware requirements stem from improved resource utilization and the ability to handle larger workloads on existing clusters. Operational costs decrease through reduced maintenance, fewer performance-related incidents, and simplified troubleshooting. Developer productivity improves dramatically through faster job completion times, enabling more rapid iteration and experimentation. The competitive advantage gained from faster insights and more responsive analytics capabilities often justifies the investment many times over. When properly implemented, Uniffle typically delivers a compelling return on investment through lower total cost of ownership and enhanced business agility. Successful Apache Uniffle implementation follows a structured approach that minimizes risk and ensures optimal results. Begin with infrastructure assessment and capacity planning to determine appropriate cluster sizing and resource allocation. Network and security configuration review ensures that connectivity requirements are met while maintaining appropriate security postures. Integration testing with existing workloads validates compatibility and performance improvements before production deployment. Finally, monitoring and alerting setup provides operational visibility and proactive issue detection. This systematic approach ensures that organizations can confidently deploy Uniffle while maximizing its benefits and minimizing potential disruptions to existing operations. For organizations seeking maximum performance from Apache Uniffle, advanced optimization techniques can deliver additional gains beyond standard configurations. Custom partitioning strategies allow fine-tuning of data distribution patterns to match specific workload characteristics, reducing data skew and improving parallelism. Memory management tuning involves sophisticated configuration of caching policies, spillover thresholds, and garbage collection parameters to optimize performance for particular use cases. Network optimization techniques can maximize throughput in high bandwidth scenarios through careful configuration of connection pooling, buffer sizes, and routing policies. Storage tiering strategies enable cost-effective performance by intelligently placing hot data on fast storage while archiving cold data on economical alternatives. These advanced techniques require deeper expertise but can provide significant competitive advantages for performance-critical applications. Apache Uniffle's architecture supports sophisticated multi-cloud deployment patterns that enable organizations to leverage the best capabilities of different cloud providers. Hybrid architectures can span multiple cloud providers, allowing workloads to be placed optimally based on performance, cost, or regulatory requirements. Geographic distribution strategies can minimize latency for globally distributed users while maintaining centralized shuffle management. Disaster recovery and business continuity planning benefit from Uniffle's fault tolerance capabilities, which can span across different cloud regions and providers for maximum resilience. Cost optimization becomes possible through intelligent workload placement that takes advantage of different pricing models and performance characteristics across cloud platforms. These deployment patterns make Uniffle an ideal foundation for modern, flexible cloud-native analytics architectures. Containerization and orchestration play crucial roles in modern Apache Uniffle deployments, particularly in cloud-native environments. Kubernetes deployment best practices ensure optimal resource utilization, scaling behavior, and service reliability through proper pod sizing, resource limits, and health checks. Docker container optimization focuses on minimizing image sizes, reducing attack surfaces, and configuring appropriate runtime parameters for shuffle-intensive workloads. Resource orchestration and scheduling considerations involve configuring Kubernetes schedulers to understand Uniffle's resource requirements and placement preferences. Service mesh integration can provide enhanced management capabilities including traffic control, security policies, and detailed observability. These containerization strategies enable organizations to deploy Uniffle with the agility, scalability, and operational efficiency expected in modern cloud environments. Effective benchmarking and performance testing are essential for maximizing Apache Uniffle's benefits and validating deployment success. Standardized testing methodologies enable meaningful comparisons between traditional shuffle mechanisms and Uniffle implementations, providing concrete evidence of performance improvements. Workload simulation techniques create realistic performance assessment scenarios that mirror actual production workloads, ensuring that optimizations translate to real-world benefits. Comprehensive metrics collection and analysis provide the data needed for ongoing optimization efforts, helping administrators fine-tune configurations for specific use cases. Continuous performance monitoring and validation ensure that systems maintain optimal performance over time as workloads evolve and scale. These benchmarking practices form the foundation for data-driven optimization and sustained performance excellence. Security and compliance considerations are paramount for enterprise Apache Uniffle deployments handling sensitive data. End-to-end encryption protects shuffled data both in transit and at rest, meeting stringent data protection requirements across industries. Robust authentication and authorization frameworks ensure that only authorized clients and administrators can access shuffle services, with granular permission controls for multi-tenant environments. Comprehensive audit logging captures all critical operations, providing detailed records necessary for regulatory compliance and security investigations. Network security and isolation mechanisms protect against unauthorized access and data exposure, including support for secure network zones and encrypted communication channels. These security features make Uniffle suitable for deployment in highly regulated environments where data protection and compliance are non-negotiable requirements. Disaster recovery and high availability planning ensure that Apache Uniffle deployments maintain reliability even during unexpected events. Automated failover and recovery mechanisms enable the system to continue operating smoothly when individual components fail, with minimal impact on running workloads. Data replication strategies provide durability guarantees by maintaining multiple copies of critical shuffle data across different servers or even data centers. Backup and restore procedures protect against catastrophic failures, ensuring that critical data and configuration information can be recovered when needed. Regular business continuity planning and testing validate these recovery mechanisms and ensure that teams are prepared to respond effectively to various failure scenarios. These capabilities are essential for production environments where uptime and data integrity are critical business requirements. Comprehensive monitoring and alerting strategies are essential for maintaining optimal Apache Uniffle performance and reliability in production environments. Key performance indicators track system health metrics including shuffle server availability, data transfer rates, memory utilization, and job completion times. Real-time alerting mechanisms proactively detect potential issues before they impact workloads, enabling rapid response and minimizing downtime. Capacity planning and resource utilization tracking provide insights needed for scaling decisions and performance optimization. Integration with existing monitoring ecosystems ensures that Uniffle metrics fit seamlessly into organizational monitoring practices and tool chains. These monitoring strategies provide the visibility and control needed to maintain high-performance, reliable Uniffle deployments that meet business requirements consistently. Effective troubleshooting and debugging capabilities are crucial for maintaining Apache Uniffle performance and resolving issues quickly. Diagnostic tools provide detailed performance analysis capabilities, helping administrators identify bottlenecks and optimize configurations. Log analysis techniques enable systematic issue identification by correlating events across different system components and time periods. Network troubleshooting capabilities help resolve connectivity problems that can impact shuffle performance and reliability. Resource contention and bottleneck detection tools identify performance-limiting factors and suggest optimization strategies. Mastering these troubleshooting techniques ensures that operational teams can maintain high system performance and respond effectively to issues, maximizing the benefits of Uniffle deployment while minimizing operational overhead. Performance tuning guidelines help organizations maximize the benefits of Apache Uniffle through careful configuration optimization. Memory configuration plays a crucial role in shuffle performance, requiring careful balance between keeping hot data in fast memory storage while managing spillover to disk when necessary. Network optimization techniques can significantly improve throughput in high-bandwidth scenarios through proper buffer sizing, connection pooling, and routing configurations. Storage backend selection and configuration must align with specific workload requirements for performance, durability, and cost considerations. Workload-specific tuning recommendations provide guidance for optimizing Uniffle configurations for particular use cases including ETL pipelines, machine learning training, and real-time analytics. These tuning practices enable organizations to extract maximum value from their Uniffle deployments while maintaining operational efficiency. Integration testing best practices ensure successful Apache Uniffle deployment while minimizing risks and validating expected benefits. Compatibility validation confirms that existing frameworks and applications work correctly with the new Shuffle service, preventing disruptions to current operations. Performance benchmarking establishes baseline metrics and validates expected improvements, providing concrete evidence of deployment success. Security and compliance verification procedures ensure that the system meets organizational and regulatory requirements before production deployment. Disaster recovery and failover testing validate the system's resilience and ability to maintain operations during unexpected events. These comprehensive testing practices provide confidence in Uniffle deployments while identifying potential issues before they impact production workloads, ensuring smooth transitions and successful outcomes. As we conclude our deep dive into Apache Uniffle, it's clear that this technology represents a fundamental advancement in distributed computing shuffle mechanisms. The architectural improvements over traditional approaches address long-standing performance bottlenecks that have limited big data workloads for years. Organizations adopting Uniffle consistently report massive performance gains, with job completion times reduced by up to 80% in many scenarios. Enhanced reliability and fault tolerance capabilities ensure that these performance improvements don't come at the cost of system stability or data integrity. Perhaps most importantly, Uniffle provides a future-proof foundation for modern data architectures, supporting cloud-native deployments, containerization, and evolving workload requirements. For organizations serious about optimizing their big data infrastructure, Apache Uniffle represents an essential technology that delivers immediate value while supporting long-term strategic goals. Thanks for joining me on this comprehensive exploration of Apache Uniffle and its transformative impact on distributed computing workloads. If this deep dive helped you understand how remote shuffle services can revolutionize your big data processing, please hit that like button and subscribe for more technical content. Your engagement helps me create even better tutorials and reach more data engineers and architects who can benefit from these cutting-edge technologies. Don't forget to check the video description for links to Apache Uniffle documentation, GitHub repositories, and additional resources to help you get started with your own deployment. Join the growing Apache Uniffle community to connect with other practitioners, share experiences, and stay updated on the latest developments. Until next time, Keep optimizing your data infrastructure and pushing the boundaries of what's possible with modern distributed computing. And that wraps up our explanation. If you found this useful, please hit the like button and share it with a fellow developer. Don't forget to subscribe for more technical tutorials. Thanks for watching, and I'll see you in the next one.